This is chapter number 14, Operations on Bits. We have dealt with characters, integers, the floats and certain variation. And the smallest element in the memory is basically bit, but the memory content is termed in terms of byte. And we have already done it because we were handling the char. We were taking char into our program. But we must know how individual bits work, because if we are able to manipulate, then we are going to bit level, that is we are using or applying our programming to interact directly with the hardware. This is because the programming languages, they are byte oriented and the hardware, it is bit oriented. So how this byte is, how it is constructed, how we can manipulate, we'll see about that. Bitwise operator, this is one of the most powerful feature of C, which is bit manipulation operators. And we can access and manipulate the individual bits with a piece of data as a programmer. There are various bitwise operators which are available with us. This is ones complement, right shift, left shift, bitwise AND, bitwise OR and bitwise XOR. These all are available to us. They operate on integer and characters, but not on floats or double, right? So before moving on to actual details of operator, let us see we'll talk about the bit numbering scheme of integer and characters. This is how this is. If it is a character, it starts from 0, means first bit will be placed here, next here, like this. In the 16-bit, because 16-bit we are talking about 2 byte. 2 byte means 16-bit. 1 byte contains 8 bit, so 1 byte means 8 bit, so 2 byte will be 16 bit. So this is 16-bit integer. We'll use a function called show bits, and show bits is simply giving you, or it will give you the binary equivalent of the decimal. That means if I take 11, this is a decimal number. So how to get the binary equivalent? Let me show you. We divide it by 2, 2 5s are 10, remainder is 1. 2 2s are 4, remainder is 1. 2 1s are 2, remainder is 0. So we take this way, how it is written, 1 0 1 1. One more way to show this is, 1 is what? This is 2 to the, this location is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3. So 2 to the power 0 into 1, 2 to the power 0, 2 to the power 0 is 1 only, 1 into 1 is 1, plus 2 to the power 1 into 1, 2 to the power 1 is 1, 1 into 1 is 1, oh sorry 2, plus this 2 to the power 2 into 0 is 0, 2 to the power 3 into 1 is 8. So 8 plus 2 plus 1 is 11. This is how the binary things work. Let us take a simple example. That is, we want to print the binary equivalent of integers if you are using show bits function. This show bits function is just taking from 0 to 5. Just ignore this. From 0 to 5. And we are just printing this j, the decimal of this j as binary. So show bits function will take one by one from 0 to 5 and it will display the binary equivalent. These are the binary equivalent. And I just suggested you how we can find out the binary equivalent of 11. In the similar way, we can find out the value of, say, 5. 5 is nothing but 4 plus 1. So 2 to the power 0, this location will be there. 2 to the power 1 location will not be there. And then we have 2 to the power 2. Yes, the location is there. 4. 2 to the power 2 is 4. So this will be 1, 0, 1. This is the 5. Ones complement operator. We are taking ones complement. What is the ones complement? We are just making 1 to 0 and 0 to 1. This is the only ones complement operator. So if you have, say, 65, the binary equivalent of 65 is this in the 16-bit or 2 byte terms. How to find the binary equivalent? Just take this 0 to 1, make this 0 1 1 1 1 1 1 1, then this is 1, this becomes 0, 1 1 1 1 1, this becomes 0. So it will be this one. So this ones complement operator is represented by this tilde sign or tilde sign. You can find it on your keyboard above 6. Press shift and press 6, you will get this sign. This is the program for the same. From 0 to 3 we are moving and we want to find out the binary. So this is j, we are passing it to show bits. As I suggested that show bits is going to give you the binary equivalent. So once this number comes j, we are just complementing it and passing it to k and then show bitting or showing the equivalent of k as the complemented version. So this is how 0 is this. The complement, all zeros will become 1. So we are just simply doing one thing. Or show bits, after taking the binary equivalent from show bits, we are doing with tilde sign only one thing. 1 we are making 0, 0 will make 1. So what is the real world scenario use of ones complement operator? See, there are changes. When we change the original number, sometimes it's beyond recognition, and we can just use this concept in file encryption utility. This is the most basic file encryption. So we are using a file encryption or a function in this file. This is a function. What it is doing, we are taking the source file and target file. Say here we have a 0, 1, 1. We are just complementing it, making 1 to 0, 0 to 1, 1 to 0, and 1 to 0. So this is the simplest encryption we can have. This is the first file we are trying to open as a read mode, this one, and the second file we are opening as a write mode. Now we are checking for the properness. If it doesn't, we come out. Otherwise, we take one by one character from the source file, check it for end till we go to or reach end, and till the time we reach end, we take the tilde of ch, that is, we are complementing the characters and transferring it to the target file. So this is what we are doing, and please remember that the end of file ASCII equivalent is 26. Right shift operator. The right shift operator is shown by this sign, double angle, and when we want to shift. So when we want to shift, we need two operands. It shifts each bit in the left operand. Means if we have two operands, so this left operand to the right by this number. So the number of places the bits are shifted, it depends on the number which is following the operator, this operator. Okay, that is its right hand. I'll show you. This is CH, and this we want to shift thrice. We want to shift all the bits in CH 3 places to the right. Similarly, we want to shift CH, the content here, shift to 5 places. For example, if CH has a pattern this one, the simplest thing is we want to shift it to 1 when on the right. So what will happen? Say we have an imaginary place here. One will go here, one will go this place. This will shift one by one, one by one, one by one, one by one. So this place will remain empty. So we'll make it as a 0. We'll pad a 0. So the simplest or the easiest way to understand this is just remove this and put a 0 here. This number is being right shifted. So the bits are right shifted. The blanks are created on the left. That is why we placed a 0. We'll see a program. This program is doing nothing. It is just taking 5225. We have passed this I to show bit so that the binary equivalent of this can be obtained. And from 0 to 5, that is, we want to shift first time 0. Then 1, then 2 till 5. And we want to shift this number 5225 from 0 to 5. So this is the shifting. I'll show you. This is the original number. If you want to shift it to 0, the original number remains same. But if you want to shift 1, see, just remove this, add a 0 here. If you want to shift 2, just remove these two, add one more 0 here. If we want to shift 3, remove three numbers and add a 0. 4, remove 4 numbers, add a 0 here. 5, remove this, add a 0 number here. You can observe whatever I have told you, you can easily find it here. One more thing, if the operand is a multiple of 2, then if you shift the operand 1 bit to the right, it is similar to dividing it by 2. That is, if this is 64, we are shifting it once. So 64 by 2, that is nothing but 32. When we are shifting it by 2, so we are essentially divided by 2 square. So this is 64 by 4, which will give you 16. 128, we are operating with 2. So we divide it by 2. So what we are doing here is 128 divided by 2 square, which is your 32. But because these numbers are not multiple of 2, so you will get the normal way we have just seen, 13 and 24. Left shift operator, similar to the right shift operator, which was this. The difference between the bits which are shifted to the left in this left shift operator, and for each bit shifted we add a 0 on the right. This is a program where I is 5225. So we'll pass this I to the show bits function. This show bit function will find out the binary equivalent of this 5225, and then from 0 to 4, that is, one time we want it to shift by 0, then 1, then 2, then 3, then 4. So if you see, the shifting is done as a left shift operator. So how to left shift? First of all, we want to shift this binary equivalent with 0. So there will be no change. If you want to shift it as 1, so what you have to do, just eliminate this, add a 0 here. You want to shift 2, eliminate these two, add one more 0 here, and likewise. So we have left shift and right shift operator we have seen, and the utility in the operating system, the date on which the file is created or modified, this is stored as a 2-byte entry in the 32-byte directory entry of that file. So this is the representation of that 2-byte entry of the date. So this 2-byte entry is made of the time of creation, you can say, or the modification of the file. In the operating system, it doesn't store the date, that is day, month and year of a file creation. It doesn't store it as a 8-byte, but it is codified like a 2-byte entry. So you are saving 6 byte This is 8 byte, this is 2, only using 2 bytes, so you are saving 6 byte for each file entry in the directory. And the bitwise distribution, as you see here, of month, date is in the form of 2 byte entry is like this. From this point to this point, this is year. From here to here, it is month. And from this point to this point, this is date. So the DOS or Windows converts the actual date in a 2 byte value. We have a formula like this. So we have to put a year here, month here, date here, and you will get the date. Suppose the date is like this. This is your year. So this is your year. You have to place it in this place. Then you have month, which is the third one. You have to place it here. And this 09 is the day. So when you find it out, you get a number called 5225. And the binary equivalent of this 5225 is this. And this binary value is now placed in the date field in the directory entry of the file, like this. So, as you see, 5225, we have already seen the binary equivalent. So this is 0001, as you see here, 0100, 0100, then 0110, that is 0110, and 1001, like this. In order to verify, just see the month 0011, and you find the binary equivalent or decimal equivalent of this binary, you will get a 3. This, in this similar way, the day and years can also be verified. If you open the Windows Explorer, if you are using Windows, then the date is again, because the content is stored as a 2 byte. So when it is being taken out, you will see the date in the format of MMDDYY. So how does this conversion take place? This is only by using the left shift and right shift operator. So let us see how this bit pattern is seen of year, month and day. And this is in the contiguous location. And we want to separate them, that is year, month and day. And we apply the bitwise operator. For example, in order to get year as a separate entity for 2 bytes, we just right shift the entry by 9. See how this is the actual entry. Now we are shifting it to 9. So this is shifting to 9, and what we are shifting? We are right shifting the content, means we are eliminating the 9 content. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the content you see here. This is how many? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And these are your year. From this point to this point, you get the year. Similarly, if you left shift by 7 and right shift by 12, you get the month. This is first we are left shifting by 7, means this side, and then we are shifting 12 on the right side. This portion you get this exactly. You get 0011, which is your actual month. Then for obtaining the day, we left shift date by 11, then we right shift the result by 11, and left shifting of 11, as you see in the diagram, it gives you this content. And right shifting will give, if you right shift by 11, you get this bit stream. And the entire logic can be seen like this. We are decoding date field in directory entry using the bitwise operator. So this is, if you have a date as 9, month as 3, and year as 1990, just put this inside this, so you get the date. And you can just print the date, and if you want to find out the year, add 1980 with the date which is shifted rightwise to 9. Then you can shift the date left 7 bit shifting, and then the result should be shifted right to 12. This is your month. Similarly, the date can be shifted 11 on the left, and then 11 on the right, you get the date, and you can just print it. So this is the sample run of the this logic. Bitwise AND operator. This is the AND operator. So it is not equivalent to double AND, which is the logical AND operator. So this AND operator operates on 2 operands, and when we are operating on this, we go bit by bit. So if both the operands must be of same time, they must be, if one is character, the other has to be character. Similarly for integer. The second operand is called the AND mask. We'll see what this masking means. This AND operator operates on a pair of bits, and it results only bits. Okay, so the rules that decide the value of the resultant is like this. If we have 0.0, you get 0. Means anywhere you find 0, you'll get 0. See, here you have 0, you have 0, you have 0, you get 0. Otherwise, when only 1 is on the both side, you get 1. And this can be easily represented here also. This is the logic and you can say 0, 0, 0, 0, 1, 0, 1, 0, 0. Only 1, 1 will give you 1. Let us see what happens here. This is the first one, this is the second one, and we want to AND it. We just saw that if only 1, 1 is there, you get 1. Otherwise, if any of the bit is 0, you get 0. So see, 0, 1, you get 0, 1, 1, you get 1, 0, 0, you get 0, 1, 0, you get 0, 0, 0, you get 0, 1, 0, you get 0, 0, 1 you get 0 and 1, 1 you get 1. So this is the result. And apart from this, you can do one more thing. You can use AND operator to check whether certain bit is on or off. On means 1, off means 0. So we'll see about that. For example, you have a bit pattern like this, and we want to check whether this bit number 3 is on or off, because we want to check the third bit. So you just have to see or place 2 to the power 3, that is 8th, this 8th, or which bit is giving you 8 value, that is this one. You just have to put this as 1 and this content, others are 0, only put 1 here and AND it with this one. So what you get, the ANDing will give, this is the AND mask, and why we are ending with this content, because this is the third bit we want to check whether it is on or off. So when we AND it, we get 1 here, and we are ending with this, we get 1. That means this bit is on. This bit is on. This is the whole logic here, right? I hope you got the idea. If I wanted to check this one, say this one, I will place a 1 here, other 0, and because 0 and 1 will give me 0, that means this is off, and this is what we wanted. And just a program to test whether a bit in a number is on and off. This is, say, some number, and we just ANDed it with 32. And if j is 0, 32 means 2 to the power 5, that is 32. So you know which bit has to be placed. This is 1, this is 2, this is 1, this is 2, this is 4, this is 8, this is 16, and this is 32. So this has to be made 1, other 0. 1, 2, 3, 4, 5, 6, 7, 8, like this. This will be the mask. This will be the mask. And when you do it, the 5th bit is off, otherwise the 5th bit is on. And you want to check the 6th bit now, because this was 1. You now place this one, this has 1 and this has 0. So the 6th bit is off if you get j equal to 0 after ANDing this. Otherwise the 6th bit is on. And this is the sample run of this program. So in the file entry in the directory, we have an attribute byte, and this is the attribute byte, as you can see. The status of the file is governed or indicated by the value of individual bits in this attribute type. The AND operator can be easily used to check the status of the bit of this attribute byte. For example, this is the attribute byte. If this first bit is 1, that means this file is read only. If the second one is on, that is it is hidden. Third means system, and likewise. Okay, so you can easily use or check whether a particular bit is on and off for this byte stream to know whether the file is read only, whether the file is archived, like this. And one more thing which is very important with AND operator is you can change the status of the bit, or you can switch off a particular bit. How to do that? If the first operand is this, you want to switch off particular bit, say bit number 1, this one. Okay, so just place, this is the mask. If you want to put this or make this as off, you put 0 here, all others as 1, because we know when we AND it, 1 and 0 will give you 0. So this one will become 0, this one will become 0, and this will be off. Otherwise there will be no effect with 1. So AND has actually made that particular mask which we have used, has actually made that content as 0, because we have used 0. So we can particularly go to some bit and switch it off, make it as 0. So let us summarize what this AND operator has done for us. First of all, we can use it to check whether a particular bit in a number is on or off, and it is used to turn off a particular bit in a number. Bitwise OR operator. This bitwise operator, another important bitwise operator, which is shown by pi, which is the OR operator. And what are the rules? See, if 0, 0, there is 0. 0, 1, that will be 1. 1, 0, that is 1. And 1, 1 means 1. So every time you get at least 1, any 1, you get always 1. So 1, 0 or 0, 1 or 1, 1 will always give you 1. 0, 0 will only give you 0. The truth table is something like this. Say 0, 1, as I said, this is OR. So you'll get 1 because at least 1 is there. So only this 0, 0 is going to give you 0. This 0, 0 is going to give you 0. Otherwise everything is 1 only. So this bitwise operator is also used to put on a particular bit in a number. So suppose we have a bit pattern like this, and we want to put on a bit number 3. So this is the bit number 3. This is 0, 1, 2, 3. So this is bit number 3. Now you want to switch this as on. So just place 1 here in the mask, other 0. And now just OR them. Just OR them. Bitwise OR operator. In the OR operator, what happens? If you have 0, 0 or 1, 1, if both are equal, you get false. You get false. Otherwise, if you have 0, 1 or 1, 0, you get true. So this OR operator is represented by this cap. In the keyboard, you can find it over 6. And this is also called as exclusive OR operator. This will return 1 when any one of the two bits or both the bits are 1. Otherwise, it will give you 1 only if one of the two bits is 1. So the truth table is simply like this: 0, 0, 0, 1, 1, 0, 0, 1, 1, and 0, 1 is 1. So if you both are same, see 0, 0, both are same, you get 0. If both are same, 1 and 1, you get 0. Otherwise, you get 1. So this XOR operator is used to toggle a bit on or off, right? And the number which is XORed with another number is actually twice the original number. So this is a program. We have used some number and we are trying to OR it with it, and the result, you can easily get the result like this. So you can give a sample run to this program, okay? And this is the actual XOR operator. Again, let me remind you, 0, 0, 1, 1 will always give you 0. 0, 1 or 1, 0 will give you, this is the pipe, will give you a 1. Okay? Show bits function. This show bit function is simply taking a decimal number and giving you the bit stream. Say, let me take 15. So what will be the value of this decimal number in terms of bits? 2 7s are 14, remainder is 1. 2 3s are 6, remainder 1. 2 1s are 2, remainder 1. Okay. So we go from this side to this side. So you get 1 1 1 1. This is the binary equivalent of 15. Show bits, in the show bits function you pass 15, you get 1 1 1 1. So this is what is happening here is, we are starting from 15, you are going till the 0, and you are ending it, or you can say you are left shifting this 1 with I. And now this AND mask, every time this AND mask will change, and now AND masking is done with N. So if it is 0, you print 0, otherwise you print 1. So every time you print 0 and 1, you get a bit stream, which is equivalent of the decimal number which you pass in this function. So this is the AND mask, and as we just said, that you are just left shifting by 15 places. If the variable n, the most significant bit is 0, the k would contain a value 0. Otherwise, it would contain a non-zero value. So if k contains 0, then the printf will print out 0. Otherwise, it is going to print 1. And in the similar way, you are going for the second loop, this I is decremented again. Hence, this AND mask every time changes. So we'll now have this one. First, it was here. Second, it was here. Next time run, 1 will be this, 0 will be this. So this will check whether the next most significant bit is 1 and 0, and it will print it accordingly. And then similar operation is repeated for all the bits in the number. So let us summarize what we have seen. In order to manipulate the hardware-oriented data, the individual bit rather than the bytes are set these are the set of bitwise operators which we can employ. The bitwise operators, this include operations like ones complement, right shift, left shift, bitwise or and or and XOR. The ones complement will convert simply 1 to zeros, all the ones to zeros, all zeros to 1. And the right shift, that is the right shift, and the left shift operator, they are very useful in eliminating the bits from number, either from the left or the right. We have a bitwise AND operator. This is very useful for testing whether a bit is on and off. And also you want to put off, make some bit 0. This is also done by AND operator. The bitwise OR operator is used to turn on the particular bit. And this XOR operator, this is similar to the OR operator. Just if you have 0, 0 or 1, 1, you get 0. Or if you have 0, 1, 1, 0, you get 1. So this is all about this chapter. Thank you so much and take care of yourself.